Let's take a look at this rates of reactions question. The question reads, the reaction of copper carbonate with excess dilute HCl is used to investigate the rate of a reaction. The balanced equation is given. They give us the equation, they also give us the apparatus, and they want to know, state two ways in which the rate of the reaction can be increased. 5.1, you can always increase the rate of a reaction by increasing the temperature. Right? Secondly, we can increase the rate of a reaction by using a catalyst. So they wanted two. Let's just keep it simple and move on. Next, we have a graph, and the question says, during the investigation, samples of both pure and impure copper carbonate of equal masses are used. The graphs below are obtained from the results. Now, let's just color coordinate it just so it's easy to follow. Let the impure be green. And so let the pure be blue. Now the question says, write down the reaction time for the reaction of pure copper carbonate with HCl. Now what we're looking for is we want to find where the line straightens out, or where does it become parallel to the x-axis. So if you're following this blue line, and we're looking for where the line more or less straightens out, that's going to be roughly here in this region right here, because you can see more or less from here it straightens out. So where it straightens out, that's where the reaction stops. So our answer in this case is going to be roughly 50 seconds. So question 5.2, roughly 50 seconds. Okay, question 5.3. Assume that all the gas formed during the two reactions escape from the flask and the impurities do not react. Okay. 5.3.1, calculate the average rate of the reaction. Okay, we've done that. 5.3.1, calculate the average rate of the reaction for the pure sample over the first 20 seconds. So this question is asking us to calculate rate, and to calculate rate, we can use the formula. Rate is equal to the change in the mass, since we have mass on the y-axis, divided by time. Now, they've asked us to calculate the rate for 20 seconds, so 20 will be in our denominator. Now, we need to figure out how much the mass changed by. So, the mass was 170, and then at 20 seconds, we don't know the mass, but we can read it from the graph. So, at 20 seconds, now we're following the blue line, 20 seconds, more or less there, we want to know what's the mass going to be. Now, since this is a graph with the grid lines, we do need to calculate the exact amount. Now, it may be a bit difficult to work out what the intervals are here. So what you can do is you take these two spaces, so the values that are known, and you subtract them. So you'll say 169.8 minus 169.75. That gives you 0.05. Now you divide that by the number of blocks that's there. So if you count, the number of blocks between this point and this point is 10. So you divide that by 10, that means each block is 0.05. Now from here to here, you're going up by 2 blocks, so you're going to add 2 times 0.05. And so what you're going to have here is 169.76. And that's the amount that's left after 20 seconds. So we can then substitute that value in here, 169.76, and then that will give us an answer of 0.012 grams per second. And that's our rate. 5.3.2. So 5.3.2 reads, calculate the percentage purity of the impure sample. Now, to calculate the percentage purity, we do need to know how much of the impure was used and how much of the pure was used. So let's start with the impure, since that's there. So the mass of the impure, right? It's going to be 170, so that's how much it started with. and then minus what's left at the end. So at the end, we need to figure out what's this value here going to be, right? And if we know that this right here is 169.75, we can figure out what this is by again multiplying by the number of blocks, right? So this point right here would be 169.78. To use white here, 169.78, and so we can subtract this. So 170 minus 169.78, and that gives us 0.22 grams that reacted, right? So that's the grams that reacted. And remember, that's going to be the pure mass. Even though it says impure, the amount that reacted is going to be pure. So this is the reacted, so this is actually the pure value, right? Now we can work out the mass from the impure graph. Sorry, from the pure graph. That's going to be 170 minus, now we're looking at this blue one, we're going to figure out what is this. So that's going to be, if we look at the start, 169.70 is here. Then this point right here is going to be 169.73, right? And so we can subtract this 169.73, and that gives us 0.22 grams. Not 0.22, sorry, 0.27 grams. Okay, so to calculate the percentage purity, you take the smaller mass divided by the bigger mass times 100. So the percentage purity is going to equal 0.22 divided by 0.27 multiplied by 100. And that's going to give us 81.48%. Okay, so you can think of it like this. The pure represents the maximum amount that could have reacted, so that's 0.27. The 0.22 represents the amount that did react from your impure. And remember, only the pure reacts. So 0.22 was pure out of 0.27. So you can then work out the percentage purity. Then next one, 5.3.3. The question reads, calculate the maximum volume of CO2 produced during the reaction of the pure if the reaction takes place at standard conditions. Okay, so first thing we need to do is we need to calculate the number of moles from the copper carbonate, CuCO₃. Now we know the mass that reacted, that's 0.27 grams reacted, divided by the molar mass of copper carbonate is 44. That gives us 6.13 times 10 to the minus 3 moles of copper carbonate that reacted. Now we need to do a mole ratio, right? So the mole ratio of copper carbonate to CO2 from the reaction, let's see, copper carbonate to CO2 is 1:1. So 1:1. So that must mean that the number of moles of CO2 is going to equal 6.13 times 10 to the minus 3. Now that we know the number of moles of carbon dioxide, we can calculate the volume. So number of moles is equal to volume divided by molar volume. The number of moles is 6.13 times 10 to the minus 3. That's equal to the volume, which is what we want. And molar volume at standard conditions is 22.4. You then cross multiply to solve for V. V is equal to 0.137 dm cubed of CO2. And moving on to the last question now, the question reads, sketch a graph of the volume of gas produced versus time for the reaction of pure CO2. Indicate the reaction time on the x-axis. So we did say that the reaction ended approximately after 50 seconds. So time will go here, and then volume will go here, right? And we worked out the volume to be approximately 0.137. And this is dm cubed, and this is in seconds. So the reaction will start off, we'll have a high rate, and then at 50, it should taper off straight. So it should look something like that. Okay, thanks for watching. I'll see you in the next one. Bye-bye.